Okay, electronegativity. Bonds, we talk about atoms sharing electrons in a covalent bond, but they don't do it equally. Each atom has its propensity for pulling electrons towards them. That's electronegativity. And the one that likes it, if you look at your chart in your book, you see fluorine has below it in the electronegativity chart, it has 4. That's the highest electronegativity. It goes from 0 to 4. I think the lowest one is 0.7. Yeah, that's all. That's the lowest one that I see. So we can even say it just goes from 0.7 to 4. But it's a relative scale. There's no units of measure. What this is just saying is that fluorine is the largest. And if we look for it, we have boron, which is 2, and we can take this to mean that fluorine is when it pulls on electrons, it does it twice as strongly as boron. It likes electrons twice as much as boron. Then we have sodium. Lithium is 1.0. So boron likes electrons twice as much as lithium. Fluorine likes them 4 times as much. So if these guys are in the same, are bonded together, then the fluorine is going to pull on the electrons more than boron and more than lithium. And so the electron density is going to be shifted towards the fluorine, causing one side to be more negative than the other. And that's where the polarity of a bond comes in. So let's take a look here. You might imagine for 2 hydrogens that they both pull on the electrons equally, and that the true shape here of the cloud, since the electrons aren't just between the hydrogens, that's where they mostly are, but they go all over and form like a capsule. And it'd be a nice, evenly evenly distributed cloud, a very symmetric looking form. And hydrogen, each of these has 2.1. So what we do is, make sure I get the... they don't really show, well, they use X, but the change in electronegativity, which they label as X, yeah, we won't even do that. Now, just the change in electronegativity it would be 2.1 minus 2.1 equals 0. This is what we'd call a nonpolar covalent bond. This is generally only going to happen between 2 of the same atom, but if you look in the chart, there's a lot of the elements that have the same electronegativity, so that could happen for them as well. So what you want to do is take the electronegativities of each atom that's part of the bond and subtract them, and take the absolute value, it doesn't matter which way you subtract them, and then if it turns out that the value is 0, the change in electronegativity is 0, then it is nonpolar, that both atoms are pulling on the electrons equally. Now look at hydrogen chloride. Hydrogen is 2.1, chlorine is 3.0. That means that the chlorine is pulling on the electrons more so than the hydrogen, which means that it's shifting them towards itself. So instead of having this nice equal kind of capsule or cloud of electrons, they're more around the chlorine than the hydrogen. So how we show this is that the chlorine is slightly negative and the hydrogen is slightly positive. So you can use these little del symbols, or sometimes people use the polar arrow. So you could do that, or you could do this to indicate that they're which side is more polar. And don't use both of them. Normally you just use one or the other. Now, let's see. Since now let's take the delta for the electronegativity. We have 3.0 minus 2.1, and that's 0.9. This would be a polar covalent bond. If it is anything but 0, but it's less than 2, then it's going to be polar covalent. Now, different books have different ranges of what is a polar bond and what's an ionic bond. But generally, let's take something that we know to be an ionic bond, sodium fluoride. Look at sodium and fluorine. We could put the electrons between them, but we know that they lie completely on fluorine. These are, and let's just prove that with this change. So we have 0.9 and 4.0. So the change in electronegativity between them is 4 minus 0.9. If you made it 0.9 minus 4, you just end up with the negative, and I said take the absolute value. 3.1, that's greater than 2, so this would be ionic. Now the reason I'm looking around in your book to see what they use as their cutoff for ionic compounds. It changes from book to book. I'm going to go with around 2. On the exam, I would make sure that it's way over 2. Make sure that just looking at it, you know that it's ionic. But when you have that big of a change, it's not polar. It's the electron has absolutely been shifted from the metal to the nonmetal. What about boron? So we did this one, this one, this one. Boron fluoride. Now you say, well, there's no molecule that's just boron and fluorine, because the boron forms 3 bonds. But that's what we're saying. We're just saying the bond. This could be the bond in this molecule, but we're just looking at one bond at a time. Once we find out if this is polar, then the other ones must be as well. But we're just talking about one bond, not a whole molecule. We'll talk about the polarity of molecules later. So just look at the bond. And we have boron is 2.0 and fluorine is 4.0. And this delta En is 4 minus 2, or 2. And so that's right on the edge. Boron trifluoride is considered to be a covalent compound, not an ionic compound. So it's riding the edge. So what we would say here is that it is a polar covalent bond. And that's why they usually say the difference has to be greater than 2.0. But if on the exam you said this was ionic, going by this number, I wouldn't hold it against you, and I just try to make sure I didn't give you something that was exactly 2. So if it's less than 2, it's going to be polar covalent, and greater than 2, it's going to be ionic, and then 2 depends on how each book is looking at that number. So carbon, our book I believe says it's greater than 2.0 is ionic. But this one with carbon bromide, you should know that these are 2 nonmetals, and that should be a covalent bond. You have 2.5. Bromine is 2.8, so the difference is 0.3. So it's not 0, so it's polar covalent. So there's nonpolar covalent, there's polar covalent, and there's ionic as far as the bond. So that's what we have to work with. So I'd give you a set of bonds. You'd have to tell me what the difference is here for the electronegativity. And how we draw this is the electron density flows from the carbon, which has a lower electronegativity, to the bromine, which has a higher one. And so you maybe draw polar arrows or these del symbols, or you just put polar covalent.